the wrong time to press the record button. Got it. So I'm sharing my screen, so I go here. And maybe it pops open. Maybe I do like this. Yes. Okay, cool. Okay. We were talking about motors and generators. And we were talking about this generator, really, where I have a magnetic field. Okay, I have a magnetic field going in a specific way, and I have a loop of wire going like this, where I've connected my loop of wire to something out here. And then I'm going to spin this loop of wire at some angular velocity, so that as it spins around, the magnetic flux goes from 0 to a maximum to a 0 to a maximum, and it keeps spinning. Then we used Faraday's law and took the derivative of the flux through that loop, and we ended up with a voltage being generated here that was time dependent. And looked like this. And I wanted to say a few more words about this. So first off, this is the number of turns. And so, of course, if you're looking to get more and more voltage, just adding an extra couple loops of wire is a super easy way to do that. Here's the magnetic field, E field. That's actually one of the harder things to mess with, because to make a magnetic field, you have to either get a really strong permanent magnet, which you have to dig out of the ground, or generate another current, which again takes energy. Area of the loop. Inconvenience, because you have to have enough space to house this loop, and the bigger the loop, the more like mechanical issues you're going to run into. And then angular velocity, or we might even call this angular frequency, where this is how quickly you're going to spin this loop. And that is something that is kind of easy to change, because once you have a mechanism to spin this loop, you can say spin faster or spin slower, and so that's not bad. So what you would do then is you generate this voltage, which is time dependent. So I'd have a voltage with respect to time that looks like a sine wave, where the maximum voltage that you're going to see is N B A omega, the thing in front of the sign, right? And this curve will go from the maximum voltage to the negative maximum voltage. Okay. And one of the things I'd like to point out here is that this is an alternating current generator, where not next chapter, but the chapter after that, we'll do some AC analysis. So far we've done DC, which stands for direct current, which means we hook our resistor up to a battery, and the battery is at 10 volts and it stays at 10 volts. And so whatever current we arrive at, it's a steady current. So like in lab, when you measured all the currents, they didn't change with respect to time. You just turned it on and then you got a current, right? Here, because our voltage is changing with respect to time, our current, like whatever we hook up to this, the current will be changing with respect to time as well. And so that's what the chapter on AC circuits is going to be about, is how we deal with that time component. Okay, I like this. I should note this angular frequency. You've probably seen it somewhere, but angular frequency is 2 pi times just regular frequency. where regular frequency is 1 over the period of oscillation. Have you guys seen this before? Okay, let me just like write it out so you have it in your head. If you remember the period, time it takes to complete 1 revolution. You can generalize this. So when we dealt with this in mechanics, we were talking about things going around in circles. For this, you can say time to complete 1 pattern. So like whatever pattern, say a sine wave you have, the time it takes to complete that is the period. So going from here to here, the time it takes to complete that is 1 period's worth of time. Sound okay? And so the frequency is literally like how frequent something is. If it takes 2 seconds to complete 1 pattern, that means the pattern will repeat at a frequency of 1 over 2 seconds, which you measure in hertz. And then sometimes, just because it seems to come up a lot, we deal with this thing called angular frequency. And angular frequency is measured in radians per second. So it's really saying, okay, we're not just, this pattern is not just any pattern, it's a pattern that depends on angles. And we consider 1 complete revolution 2 pi radians worth of angle. Everyone kind of okay there? Okay, sweet. So those are just like the things that you might need to deal with. Now, this was a generator, and so this means that this is attached to some sort of crank that someone is turning, either just with their hands or hooking it up to a windmill or something. You, of course, can have a motor, which is what the thing in the lab was, where when you have current turn on, whoosh, this guy. When you have current turn on, so you hook this up to a battery, current flows, this makes a magnetic field like that will want to line up with some external magnetic field. So like if you have a magnet here with a magnetic field going like this loop will want to turn so its magnetic field lines up with the external magnetic field. Just like the torque problems we did a week or 2 ago where we talked about the torque on a current carrying loop. That's what's going on here. And then you set it up so as it turns, part of the wires are insulated, so the current turns off. And so, but then it'll just kind of keep spinning because it's got inertia, and it'll keep spinning until it hits the current, the uninsulated part. The magnet will turn on again, and it'll kind of get a kick. And so every time it turns around, it gets a little accelerating kick until it's going fast enough that whatever friction is taking that energy out of the system, the kick is putting back in. Sound okay? But yeah, it's same exact thing, just instead of mechanical energy being converted into electrical energy, here electrical energy is being converted into mechanical energy. And should we do a problem? Okay, and the problem I think that would be really nice to do, I actually really like it, is this number 18 from the homework, where we have a coil of wire that has 500 turns, an area of 1/4 of a meter squared, and we're just going to spin it in Earth's magnetic field. So we're just like picking this up and spinning it. So Earth's magnetic field which is 5 times 10 to the negative fifth Teslas. And so we're going to spin this thing, whoosh, and we're hooking this up to some sort of voltmeter, where our voltmeter says that this is 12, that's not an R, that's a 12 kilovolts. Okay. And that's the maximum. All right, can you kind of picture this? So I literally just have a wire that I'm spinning, and I've hooked it up to a voltmeter. And my voltmeter reads 12 kilovolts. Is that a lot or a little kilovolts? In lab, what sort of batteries are you using in lab? What's the voltage on those? 6 volts, mainly 6 volts, right? Those lantern batteries are about 6 volts. So this is 2,000 times that. So it's 2,000 lantern batteries. So big, right? Okay, this is unreasonably big. And what we're going to find is what frequency in RPMs do you have to spin this thing to get 12,000 volts out of it? Okay. So mathematically, this is pretty straightforward. It's a generator. We have an equation for a generator. Since we just want the maximum, we don't need to worry about that sign component. We just need that right there. And since we're looking for the frequency F, we're going to rewrite this. Oops, I didn't need this in yellow. As 2 pi F times NBA. So we just change the omega to 2 pi F. And now we're just going to solve for F really quick. So F will be E max over 2 pi NBA. Okay. Putting in numbers, and we're gonna do a quick unit conversion as well. So I have 12 kilovolts. I have 2 pi. I have 500 turns. I have a magnetic field of 5 times 10 to the negative fifth Teslas, and I have an area of 1/4 of a meter squared. Now this will give me an answer in 1/seconds. Or how many, this will give me an answer of rotations per minute, revolutions per minute. Not revolutions per minute, revolutions per second, right? But I want RPMs, so I need to convert that seconds to minutes. So how many seconds in 1 minute? 60 seconds in 1 minute. So I say 60 seconds, 1 minute, and then I'll have revolutions on top, minutes on bottom. Okay. This is 1.83 times 10 to the 7th RPMs. Is that reasonable? Yeah. Can you conceive of spinning something so it spins 10 to the 7th time every minute? Probably not. You're approaching the speed of light there. So no, this is not a reasonable speed to spin anything. You would break your coil before you actually achieved this velocity. So not reasonable. Not reasonable. But if you did manage to spin that just in Earth's magnetic field, you would get voltage off of it. Okay, does this make sense? Okay, I want to do that. Any questions about generators, motors? You guys feel pretty good about it? Okay. Then I want to wrap this up by talking about magnetic flux and Gauss's law, where this is really something we're going to come back to when we get to the end of this class, but I kind of want to prep this. So Gauss's law, when we're talking about electricity, says, okay, if I have some surface, the flux through that closed surface is proportional to the charge enclosed inside the surface. So it said that if I had some closed surface like a sphere or a cylinder or even like a blob, as long as it was completely closed, then whatever charge I had inside of that surface would be directly proportional to the electric flux through the surface. The idea being that that electric field couldn't get out or into the surface without having to penetrate it. And so we could track that via the flux. And so this was Gauss's law for electric fields. Let's kind of think about what it would be for magnetic fields. So if I had a magnet, and let's just draw our magnet. One of the things you guys told me when we started the magnetism part of this curriculum is that all magnets have a north and a south side. If you cut it in half, you didn't get just the north side, you got two smaller magnets. And one of the consequences of that is that magnetic fields aren't radial, so they don't like just spread out. They're loops. They always make these loops, where on the inside they go from south to north, and on the outside they go from north to south, making a complete circle. And you cannot have a magnetic field that doesn't do a loop. Okay, let's draw some surfaces. So Gauss's law, we always have these imaginary surfaces. That the big thing is they have to be closed. So like, what if I drew a sphere right there? A line would come in, a line would come out. What would the total flux through this closed surface be? Or just tell it to me in terms of how many lines going in versus how many lines going out. Yeah, so if I have one line coming in and one line going out, that means my total flux is 0, because for every bit of field that comes into the surface, that has to leave. Okay, what if I made a closed surface right there? How many lines go into that surface?
Right now?
Yeah, right now.
4.
4. And how many lines go out of that surface?
4.
4. Okay. Is there anywhere that I can make a closed surface so that the lines going in don't equal the lines going out? No, right? Because we have these loops. The only way that you could have a line going one way and not the other is if it didn't loop around at some point. And so this brings us to Gauss's law for magnetism, where the total flux through a closed surface for magnetism is going to equal 0. And you can write that a little bit fancier. You can say, well, flux is really the integral of B dot dA. So the integral of B dot dA will equal 0. But it means the same thing, where because you can't have a north side without a south side, you can't have a closed surface having a non-zero flux. And that's Gauss's law for magnetism. Okay. That brings me to the end of this chapter. Any conceptual questions about this chapter? Any problems that we need to go over in the homework? I mean, I'm happy if you guys are happy. I think we've done a lot of these. Oh, wait, here we go. Just checked. It says it opens on the 17th. Interesting. Let me write that down. Fix the quizzes. I thought I had fixed this class's quizzes. Really not. I'll get it fixed by midnight. Any of this homework that we need to go over? No? You guys feel good? Okay. It's due tomorrow then. If you have any questions, you should email me. But if we're ready to go, let's talk about inductance. Okay. Next chapter. Oh, maybe number one. I'd love to do number one. Maybe number one. Chapter 13. Oh, yeah, we can do number one. We can do number one. Which it's a bit maybe a conceptually rough, but mathematically this is going to be pretty straightforward. So we have a loop of wire. That's number one. Loop of wire. We have the radius for this loop of wire, so we'll be able to figure out its area if we need to. It's in a region with magnetic field that we're going to point towards the top of this page, where the magnitude of the magnetic field is going to change at a constant rate. So B at time 1 will be 0.15 Tesla, B at time 2 will be 1.5 Tesla over a time period of 1.5 seconds. Okay, this is changing constant rate. That's going to be important. This wire has just some resistance, where the resistance is 2 ohms. And for part A, we're going to figure out the change in magnetic flux. Tesla meters, Tesla squared meters. Yeah, I'm betting we're doing Tesla's meter squared. Okay. All right. So let's so our change in flux, that's just the final flux minus the initial flux. Flux is magnetic field dot area. So this is the B final dot area minus B initial dot area initial. Would we expect in this 1.5 seconds for the area of our loop to change? Okay, so we can just pull that out of our equation. And how would we figure out our area? Pi r squared. Okay. Times pi r squared. And then if we want to figure out this change in magnetic field, we just take B2 minus B1. So I'm just going to write that as, actually, I'll write this, B2 minus B1 pi r squared. Okay, and that's our change in flux. Okay, so far so good, everybody? All right. Then part B, we're going to calculate the average EMF induced over the loop. And honestly, we don't even need to say this is the average EMF induced over the loop, because they tell us this magnetic field changes at a constant rate. And so if the change is constant, then the EMF is going to be a constant number. Does that make sense? But since we already figured out the delta phi, all we need to add in is our delta t, which you just get from there. And so whatever you got from the previous answer, so part A, divide by the delta t. And then, so now we have this loop of wire. It's going to, since I have a loop of wire and it's got an EMF induced across it, it's going to make a current. And we would like to figure out what that current is. And so if you have a voltage and you have a resistance and you want to find a current, what equation do you use? You use Ohm's law. You say the voltage equals the current times resistance, or the current equals the voltage divided by the resistance. So again, you just use, so here you're going to use part B, and you're going to divide it by the resistor. All right, did that make sense to everyone online? You guys happy? Awesome. Any other problems you want to do? Like while I'm here and have the time? Okay, okay. Chapter 14. Inductance. Okay. Actually, that was a really good problem to lead us into this. So here's the deal. We had this scenario where we had a loop of wire in a changing magnetic field. And we knew that there was going to be some current induced in this wire, because we knew that there is a magnetic flux changing, a magnetic flux. We knew that it was changing. We knew that that would generate a voltage. We knew that there was a resistance in the wire. So we knew we could get to this current, but it was going to be several steps, right? We had to go through each step. And so what we want to do with inductance is we want to just say, I want a quantity where I know I'm going to have some sort of magnetic flux here that might be changing. And I know that's going to lead me to a current. And I just want to have like some sort of multiplier to that I'm just going to call inductance, where I could like multiply the current times this inductance and get a flux, or take the flux and multiply by this inductance and get a current. Does that kind of make sense? Okay. Now, what makes it kind of weirder is we're not really going to apply it to situations like this where we have some magnetic field and we put a loop of wire in it. We're going to say, what if I have a loop of wire, like a solenoid, and I run a current through it? Will that then generate some sort of induced EMF? The answer will be yes. So let's talk about that. So I have this loop of wire. It's kind of hard to say which way it's going, but it's going up, down, and then back. So it's doing this. It's going to make a magnetic field. Which way is it going to make a magnetic field in? So whoosh that way. Does that make sense? So it's going around this way. So current, magnetic field. Oh, no. I'm going backwards here, and it's just like, I don't know, man. So I expect this thing to make a magnetic field like this. But then these loops of wire, all of a sudden they'll say, well, I have some cross-sectional area. I didn't have a magnetic field before. Now all of a sudden I do have a magnetic field. My flux has changed. And so this is going to lead me to make this EMF to try to block that change. When it makes this EMF to try to block the change, will it try to make a current in the same way as this current I just put through it, or will it try to be going the opposite way? Yeah, it's trying to, so it will try to generate this EMF to make a magnetic field that way. And so it will try to send in current in that direction. And so this is what's called a back EMF, where you have a solenoid, you have a loop of wire, they're called inductors, in your circuit, and you just flip the switch to turn it on. The magnetic field that it generates itself causes this EMF to be induced. So it's doing it to itself, and it's causing this EMF to be induced to try to turn off what you just turned on. Make sense? Okay, back EMF. So it's doing it to itself. So we are going to define what we want this inductance to be, where the inductance will talk about how this current can be made with respect to just like the physical properties of my wire. And the way we're going to say it is this. Okay. So this is my back EMF. This is rate of change of current. And this is, we're calling it inductance. And it's just my multiplier. So as the current I send in here, as whatever it's doing changes with time, it's making a magnetic field that changes with time, that makes a magnetic flux that changes with time, and that makes a EMF that tries to counteract that change. So, and instead of wanting to go through that whole chain of logic, we just want to say, if you send in a current that's changing with respect to time, multiply that by some factor of inductance, and you will get out the back EMF. And so this is a definition. I put the three lines to say that we didn't derive this. We're just saying this is what it is. I'm connecting this back EMF to the way that the current changes with respect to time. It's proportional via the inductance. Okay. So let's talk a little bit about what we're defining inductance to be. Capital L, inductance. You measure it in henries, where 1 henry is 1 volt second divided by amp. Now you might actually recognize this, where you might not actually recognize this. Sorry, I have a typo in my notes. It's not true. Okay. Okay. What I wanted to say here is it's similar to resistance. It's similar to an ohm, because it does kind of a similar thing, where if you send current into a circuit, the resistor would block the current, not block it, but try to decrease it. You send current into an inductor, the inductor is trying to block that current. So it's opposing current a lot of times. And it is very much like an ohm in that this is kind of a scalar quantity, where you want to think of this as having any sort of direction. It's just an amount. And let's look at this. So let's take this equation, and let's write it in a more useful way. Or the more useful way I want to write it is I want to take it from this di dt, and I want to talk about it in terms of flux. Because then at some point I'm going to take that flux and I'm going to say, well, now I want to find the inductance of a specific thing, like a solenoid or toroid or something that I could build. Okay, so if I start here, negative L di dt. I'm going to work towards something L equals this thing. Well, I could, of course, also talk about Faraday's law, where Faraday's law is the negative d phi dB, d phi dt, Faraday's law. And I would add on something. I've kind of played it fast and loose last chapter, where I didn't talk about this n, where n stands for the number of loops. We added it in at a few different spots, but basically, if I have 2 loops of wires, I'll have twice as much EMF. And I have 3 loops, I'll have 3 times as much, because each wire has its own area vector. Sound? Okay, cool. And this is going to become important because now we're actually going to build an inductor. It won't be so vague. And so since these are both EMFs, I'm going to take this and I'm going to set it equal to this. So I'm going to have negative L di dt equals negative N d phi dt. I'm sure you're looking at this and saying, 1, those minus signs are totally going to cancel out. And 2, I have 2 derivatives with respect to time. Why don't I just integrate both sides with respect to time? That might be a nicer thing to do. And we will. We'll integrate both sides. with respect to time? Well, um, if you're taking the integral of the derivative of something, so if I have, the derivative of x, and then I take the integral of that, what am I going to end up with? Yeah, just the original thing. So over here, I'm going to have my inductance, which is just a constant, times the current. And then on the other side, I'm going to have the number of loops of whatever I'm talking about as a constant times the magnetic flux. Okay, which brings us to exactly where we want it to be, where the inductance of anything is equal to the number of loops times the magnetic flux divided by the current that you're sending in. Okay, and this is still a really general equation. It's just this equation that we started with, written without the differentials. Um, but it's a little more useful of an equation because we're going to use it to calculate some specifics. So first off, everyone kind of happy with that? Okay. Second off, let's talk about solenoids. So at this point, you should be thinking a little bit about the capacitor chapter we did, where we first talked in general like what a capacitor is and like physically like what it means. And then we said, okay, I'd like to build a capacitor. And I don't want to have to like slap some materials together, measure its capacitance, adjust it, measure its capacitance. I'd like to say, build me a capacitor with these dimensions made out of these materials, and then I'll know it's got X amount of capacitance. Same thing here. I want to build an inductor, and I don't want to just like send a current across it and see what I get back and do that over and over again. I just would like to say, use this, make it how many ever turns long. Here are the dimensions I want, and I will know what I'm going to get out of that. So looking at this is what inductor is, and I'm hoping you're looking at that and saying that's a solenoid. So when we talk about inductors, we really mean solenoids. So let's calculate the inductance of a solenoid. Derive the inductance of a solenoid. A solenoid. Okay, so all solenoids have some length, L. They have some number of turns, N. And they have some cross-sectional area, A. If we put a current going into a solenoid, one thing that we can say is we know what magnetic field that will generate. Right? We did that like 2 chapters ago, where we figure out the magnetic field of a solenoid. And I don't know if you remember or not, but it was mu naught in I. And I don't suppose you remember what that lowercase n stood for. Say again? Okay, no, it's not a big deal. It was the turn density, right? Where if you know the total number of turns, we'll use capital N for that, but the lowercase n is the total number of turns divided by the length of your solenoid. So you could say, 100 turns per meter or something, or 10 turns per centimeter. Okay, that's pretty good. Next thing I want to look at And I'm gonna want to write this as the total number of turns per length, just because I know my inductance equation has a total number of turns. So that'll be nice to have. Next thing. So I have my inductance equation, where it's the total number of turns of this solenoid, the magnetic flux of the solenoid divided by the current. Okay. Magnetic flux, that'll be B dot A. Um, B, we are given mu naught N over L times I. And A, I'm just going to keep as A for a moment. So looking at this, anything cancel out? Yeah, so I got my I's are going to go away. My N's are going to come together. And so the inductance of a solenoid, is going to equal mu naught N squared A over L. That's an N. Okay. Put a in Henry's. Let me say, so now if I wanted to actually go order a solenoid that had a specific amount of Henrys to it, I would say make me something with so many turns with a cross sectional area of, a quarter of a meter squared, 10 centimeters long, and I would be able to predict reliably what sort of inductance that would have. However, there's also this other thing that we can talk about here, where you can write this down kind of in a weird geometrical way, where I'm kind of, did I do this right? Yeah, I did. I'm good. Where let me convert this capital N back into a lowercase n, in which case capital N would equal the lowercase n times the length. And so now this L equals mu naught N squared L squared A over L. One of these L's is going to cancel out. And so I'm going to have mu naught N squared, the area of this times the length of this. And what physical quantity does that refer to? So let me go back. If I told you I'm taking the area of this guy and I'm multiplying it by the length of that guy, what would you tell me? Meter cubed. And what's a meter cubed? A volume. So yeah, so this is really right here. The solenoid, I have mu naught N squared times the volume of the solenoid. Is that okay? Okay, we're gonna check back on that on Tuesday. Okay, cool. Let's do a few problems because I don't quite want to start the next thing until Tuesday. So let's do a few problems while we're sitting here. Let's start at the beginning and just go through. Okay, number one. I have a circuit that looks like this. Just just like when you have the ups and downs, you call that a resistor. Inductors, you just do it for a few curlies. Um, so it has an inductance. It's going to start with the switch down. So initially, the switch will be down. And so initially, our current will be 0.15 amps. When the switch is open, the current goes to 0, but it doesn't happen all at once. And that's actually something I'd like to talk about. It takes about 1/10 of a second. Because let's think about what inductors do. So if I turn on a current, they had 0 currents before, now all of a sudden they see a current, they try to block that. What if I turned off a current? They would want it to keep going, right? So they would see this magnetic flux go away. They'd say, wait, I want to go back. I want to have that magnetic flux. So they would try to push more current through in the same direction. And so that's why when you open this circuit up, your current doesn't just stop. It takes a little bit to stop because your inductor is trying to keep it going. But just like Faraday's law can't keep things going indefinitely, the longer time frame you're over, the smaller voltage you can generate. Everyone looks pretty happy with that. All right then. So let's express the magnitude of the induced EMF average over this inductor in terms of givens that we have. Now let me ask you a question. They specifically asked for the average here. Does it matter? So we did some problem earlier where it didn't matter whether we took the average EMF or not. And it didn't matter then because the magnetic field was changing at a constant rate. Do you think it is going to matter here whether we take an average or we take an instantaneous value? Now let me ask you a question. If we graph this voltage with respect to time, and this is the voltage across that inductor. So we have the current going. It's been going for a really long time. So whatever the inductor wanted to block, it's done blocking it. Now it sees this current and wants to stay the same. Then we open this switch. And so all of a sudden it sees the current go away completely. And it says, hold on, I didn't want it to go away completely. I want it to stay the same. So it comes in and it generates that voltage. Now, over time, it can't sustain that because as the dt gets larger, the EL gets smaller. And so just like after a while it was okay with current flowing, then it'll become okay with current not flowing. So we're going to end up down here like that. Now, do you think it is more likely that we're going to decrease at a constant rate, hit 0, and then change the way we are? Or is it more likely that we will decrease a lot at first and then kind of smoothly come into zero. I like the smooth answer because there really aren't a whole lot of discontinuities in physics, right? Discontinuities don't happen a lot. So we expect the smooth, continuous solution almost always. So given that our rate of change is not constant, can we just find an instantaneous value of no? Okay, we have to find an average value. Excellent, excellent. Okay. And so in this particular case, the average value truly matters. So when we're doing this calculation, where we might have started with a derivative that would give us the instantaneous value, we are going to change that to the delta I over delta t so we can get more of an average value. Okay. And at that point, we can just plug in our numbers. So let's look at that. Negative L delta I over delta t. So our L was 1.5 henries. Our delta I, we go from 0.15 to 0, and our delta t 0.11. And they specifically asked for the magnitude, so we're just going to magnitude that. I get a 1.5 henries, 0.5 amps over 0.11 seconds. And if you plug in all your numbers, you get about 2. What unit should you put on that? Voltage. I like it because we're still looking for a voltage, right? EMF is still a voltage. Let me ask you a question. So we had this situation. It was closed like this. Which way was the current going around this circuit before the switch was opened? Right? Counterclockwise, from the positive to the negative. Excellent. So this was the I before, right there. Then the switch opened. This went to 0, and this EMF was generated. Was it generated so current would flow in the clockwise direction or the counterclockwise direction? So did it want current to keep going in the same direction, or did it want to send current in the opposite direction? Online people, what do you think? No answer. Let me tell you. It wants things to stay the same. So if it saw this current going counterclockwise, it wants to keep a current going counterclockwise. So in fact, it would make a voltage that looked like a battery going that way to keep current going in the counterclockwise direction. That's everyone kind of happy with that? Okay. I might call this class a little early. There's several problems I want to do, but they're all going to take longer than 10 minutes. Yeah, I'm gonna go ahead and call it early. There's a couple problems I want to do. They're going to take a while, and right after that, we're going to do a differential equation that will also take a while. And after that, we'll do another differential equation, which will also take, well, that one will actually take less time. But since we're ahead and since that'll all be kind of hefty. Let's go ahead and call it today. Any questions before we call it? Okay, cool. Have a great weekend. If you have any problems or anything, please just let me know. Online people, are you guys okay? I don't know. Sometimes they say stuff, and then I completely miss it. Okay. Yeah, have a great weekend, guys.